Okay, so for our final section of chapter 2, we've talked about hydrocarbons and we've talked about how to draw them, how to name them. But let's talk a little bit about the properties of these alkanes and cycloalkanes that we've been looking at. So most of the alkanes, remember that is a single bonded hydrocarbon that we see in every day, are in petroleum mostly. Petroleum deposits are a very common source of these alkanes and of other hydrocarbons. For example, crude oil can be distilled over a range of temperatures, and that allows it to separate into its pure compounds. So when we take crude oil from the ground, it's distilled via temperatures, and we can get things like refined gas, which are carbons of length 1 to 4, light gasoline or naphthalene, which are carbon chains from 5 to 12, kerosene, which are carbon chains from 12 to 15, and then gas oil, which are large chains from 15 to 25. Now notice these words, you've probably seen these words like kerosene, naphtha, or gasoline, for example, and thought that it was just one particular molecule. It's actually a mixture of molecules within a range. They're all hydrocarbons. They're just separated based on their chain length. Now, some of the hydrocarbons are found in biological sources as well. Organic compounds in biological organisms have examples like pentacosane, which is a waxy covering in many insects, and hentricontane, which is found in beeswax and other natural waxes that you see. These are all alkanes, meaning again that they are single bonded hydrocarbons. Examples of alkanes in humans is rare, but it does occur. So hopane is a natural compound, biological compound that is a cycloalkane that is found in animals. Now, other hydrocarbons are very common in biological sources. They just happen to be branched with other substitutes, or they have double or triple bonds. So when talking just about hydrocarbons, pure hydrocarbons that are only single bonds, those are a little bit more rare in biological sources. So into some of the physical properties. One of the main physical properties that governs alkanes is its intermolecular forces. So I implore you to remember your intramolecular and intermolecular forces. Alkanes, again, consist of all carbon-carbon bonds that are nonpolar. They also have carbon-hydrogen bonds, which are very weakly polarized. The difference between carbon and hydrogen in dipole is very small. Since these are just generally all almost nonpolar bonds, the whole molecule itself is nonpolar. However, when you stack a lot of alkane molecules together, they exhibit something called instantaneous dipoles. And this is due to asymmetric distributions of electrons. Now remember, electrons are moving around in their electron-dense clouds, and they can be in one place at one point in time and another place in another point in time. And if they happen to be distributed unevenly, it can cause a dipole to form, a very weak dipole, but a dipole nonetheless. And if one instantaneous dipole forms in a big molecule, it can cause a nearby molecule to also form a dipole. So if one suddenly makes a little bit of a negative charge and it is near molecule B, which is nonpolar, it can cause molecule B to shift its dipole as well. Now, to get a better understanding of instantaneous dipoles, this induced force, which we also call a van der Waals interaction, or sometimes it's called a London dispersion force, I suggest you watch this video that I've attached here to look at how this shifting is occurring. But just plainly know that alkanes, long hydrocarbon chains, have these van der Waals interactions, these instantaneous dipoles that form when a lot of them are together. This affects their properties, including things like boiling and melting points. Now, the boiling points of alkanes just generally increases the bigger they get. But branched alkanes have a lower boiling point than linear alkanes. So let's talk about first those different properties. We know that boiling point is the energy that it takes to go from a liquid to a gas, right? So we have something in a liquid state and we want to bring it to a gas state. And that requires that we go from a more compact state of molecules to a less compact, more dispersed state of molecules. And I just talked about how when you have a lot of alkanes together, they have this London dispersion or van der Waals force pulling them together just slightly. So you need to have enough energy to overwhelm that force. Now, if they are bigger molecules, if they have a bigger molecular weight, they are more likely to have this force occurring. And so you need more energy to make it go from a liquid to a gas. That's why there is an increase in the boiling point. You need a higher energy, more energy, the bigger they get. Now you also need more energy if they are just linear compared to if they are branched. And that's because linear structures stack better. They can get next to each other. They have more surface area to have interactions between molecules, whereas branched chain, as shown in this example, they're a little bit more sterically hindered. They have a harder time getting near each other because of these branches, and there's not as much surface area for molecule to molecule interaction. And so the van der Waals forces between branched are just a little bit weaker, and so they don't require as much energy. They're already a little bit more separated, so going from liquid to separating them more into gas is a little bit easier. These trends are the same for melting point. So for melting point, remember we're going from a solid to a liquid. Again, you're going from something that's very packed and you require energy to make it a little bit more dispersed. So just like with our boiling point, melting points of alkanes increase with molecular weight, again, because the bigger the molecule, the more interactive force it has, molecule to molecule, and branched alkanes generally in comparison have a lower melting point than the linear alkanes for that same reason. As far as the properties of hydrocarbons and alkanes themselves, as a solid, they are typically pretty soft and waxy substances. So generally, they already have a low melting point, meaning it's pretty easy to already take them from a solid to a liquid form compared to just other compounds. Molecules that have high melting points usually have strong intermolecular forces. So we are talking about hydrocarbons having intermolecular forces, these van der Waals forces, but remember that the van der Waals intermolecular force is very weak. Now, molecules that have strong forces holding them together, like salt, for example, these have very, very high melting points. It takes a lot to get them to go from a solid to a liquid. So even though we're talking about trends in how the larger you get in an alkane, the higher the melting point or the higher the boiling point has to be. Generally, they are already pretty easy to go from a solid to a liquid and a liquid to a gas. The last property we're going to talk about is the solubility. Alkanes are very nonpolar, as we just said, and they have just a little bit of a weak van der Waals interaction. But this weak interaction can't overcome the strength of hydrogen bonds in water. So alkanes are generally just not soluble in water. Generally, they do act as a very, very nonpolar molecule. And in fact, they're so hydrophobic that they tend to cluster together and exclude water molecules away from them. You can see this, of course, in a very easy example of oil in water. You'll see oil droplets form as the hydrophobic effect occurs. One of the main chemical properties we focus on with hydrocarbons and alkanes is its combustibility. We know that alkanes react with oxygen very well. They're highly reduced forms of organic compounds because they only contain single bonds, and thus they react vigorously and exothermically, so they produce heat with oxygen. Remember, the definition of a combustion reaction is a reaction in which a hydrocarbon reacts with oxygen to form carbon dioxide and water. So we know these reactions produce a lot of heat. And generally, the larger the compound, the larger the hydrocarbon, the more energy is produced. That's just because there are more carbons and hydrogens available to break down with oxygen. And when you compare to their branched versions, for example, 2-methylpentane, 2-methylpentane actually has a total of 6 carbons in it. It has the 5 in the pentane chain and the 1 in the methyl. It's a branched form. This is a isohexane. And if you compare it to hexane itself, you'll see that it has a little bit of a lower amount of energy produced in comparison. So as a sample question, thinking about properties and alkanes, which of these alkanes has the highest boiling point? So first think about what this means. That means it takes more energy for it to go from a liquid to a gas. And we noted that bigger alkanes take more energy, and linear alkanes take more energy. To break them apart from going from a liquid to a gas. So we want to look for, of our examples here, the chain that is both the largest and the most linear, so the least amount of branching. So if we compare, if we look at our names here, simply we can just look based on the names. We have a hexane, a butane, a pentane, and a butane. So if you remember your naming, this has 6 carbons in its main chain. This has 4 carbons in its main chain. This has 5 carbons in its main chain. And this has 4 carbons in its main chain. Now, options B, C, and D have branches, which we already know we want to stick to the more linear alkane for the highest boiling point. But if we look at our branches, this has 2 methyl groups. That's 2 more carbons. This has 1 methyl group, and this has 2 methyl groups. So altogether, this one has 6 carbons, this one has 6 carbons, and this one also has 6 carbons. So we're comparing chains with 6 carbons. One has no branching, and the others all have branching. So in this case, the answer is A, hexane. The alkane with the highest boiling point is going to be the one that is linear, and it is the same size in this case, but again, you're going to be looking at bigger alkanes, more carbons will cause it to have a higher boiling point as well. Okay, so that's it for the properties of hydrocarbons, a simple and fast portion of the chapter. Just understand how those forces are interacting. I recommend you watch the videos that I posted to get a better understanding of why melting point and boiling point is affected by the van der Waals forces.